All right, here we are. I'm going to go over the first exam. We'll pull that up, walk through this. Okay, so first question, arrange the following in order of increasing boiling point. So we have three noble gases. So we want to go from the lowest boiling point, or essentially the lowest intermolecular attractive forces, to the highest intermolecular attractive forces. And in this case, we only have dispersion forces. These are all noble gases. So we're just going to go from the least heavy, or the lowest atomic mass, to the highest, which should be neon to krypton to xenon. So neon should have the lowest boiling point, followed by krypton, and then xenon should have the highest boiling point. Arrange the following in order of decreasing melting point. So going from the highest melting point, or the strongest intermolecular attractive forces, to the lowest intermolecular attractive forces. These are all very similar in terms of weight, size, and shape. We're going to start with the methanol that has the OH, that has the hydrogen bonding, followed by the CH3OCH3. That's a polar molecule, so we have a dipole-dipole. The oxygen is bonded to the carbon, so there's no hydrogen bonding, but it does have a dipole. And then lastly, the pentane CH3, CH2, CH3. That's just dispersion forces that would have the lowest melting point. So the answer there should be D, going from highest down to lowest melting point, or highest to lowest decreasing. Choose the pair of substances most likely to form a homogeneous mixture. In the first one, we have an ionic compound and a metal. So we're looking for like dissolving like. The ionic substance and the metal are not miscible in each other. Next one, we have NaI, sodium iodide. That's ionic, but the C6H14, the octet or the hexane there, is non-polar. There's no polarity similarity, so not like dissolving like. For C, I have ammonia. We have a polar molecule. We have hydrogen bonding. We have methanol, another polar molecule with hydrogen bonding. So similar, both polar, both hydrogen bonding. That should be the miscible sample there. Those should be the ones that will form the homogeneous mixture. And then just to confirm here with D, I have pentane, that's non-polar, and ethanol is polar, so not like or not similar, so no homogeneous mixture there. Place the following substances in order of decreasing vapor pressure at a given temperature. So we're looking at highest vapor pressure going to lowest vapor pressure. So the thing actually with the weakest intermolecular forces will have the highest vapor pressure. The weaker intermolecular forces are going to make it easier for the, or need a smaller amount of energy to divorce those intermolecular attractive forces for it to go from being a solid or a liquid, and then to enter and become a gas and enter into the vapor phase. So we're looking for weakest intermolecular forces to strongest. In that case, we have the OF2, maybe minimal polarity, dipole-dipole there. CH3OH methanol having hydrogen bonding, but then the NaCl being an actual ionic compound having those strong ionic bonds. So it will have the lowest vapor pressure there. So the answer there should be C in this particular inversion A. Which of the following statements is true? Intermolecular forces are generally stronger than bonding forces. No, bonding forces or intramolecular forces are much stronger than intermolecular forces. The potential energy of molecules decreases as they get closer to one another. Yes, that is actually true. They're coming closer and closer. They're starting to feel that attractive force, those intermolecular attractive forces. And so that's going to actually lower the potential energy. If they get close enough where they can get that dispersion, the dipole-dipole, the partial positive, negative charges attracting each other, that's actually going to lower the overall potential energy. Energy is given off when the attraction between two molecules is broken. No, we have to put energy in to divorce those intermolecular attractive forces. Increasing a pressure on a solid usually causes it to become a liquid. Nope, if we add more pressure, if we're pushing harder on that solid, we're only going to increase the likelihood that it's going to be a solid, not that the molecules are going to get further away and become a liquid. And then E, none of the above is true, isn't correct because B is true. 6, define sublimation. Sublimation is simply when we go from solid directly to gas. So that would be A. And then the opposite of that would be deposition, when we go directly from a gas to a solid. But for sublimation, A. For benzene, the normal boiling point is 80.1 degrees. Enthalpy of vaporization is 30 kilojoules per mole. What's the boiling point of benzene? At Mount Whitney in California, where atmospheric pressure is 456 torr. So let's go ahead and work this one out on the whiteboard. There we go. All right, so we're going to use the 2-point Clausius-Clapeyron equation again. And in this case, we want the boiling point at 456 torr. So what we can do is assume we're told the boiling point at normal atmospheric pressure, which would be 760 torr. So let's do 760 torr as our P2 and 456 torr as our P1. We're going to set that equal to negative enthalpy vaporization. I'm going to convert that from kilojoules to joules because our R is in units of joules. So that's going to be joules per mole. So we're going to go from 30.8 to 30,800. Like I said, that'll be over R, 8.314 joules per mole, Kelvin. And then 1 over T2, which we made our P2 atmospheric pressure, so we can assume the normal boiling point. We want that in Kelvin, so 273 plus 80.1 gives us 353.1 minus 1 over T1. So that's our other temperature that we don't know that we're solving for. So if I take 760 divided by 456, and I get 1.67, I take the natural log of that, and I get 0.5108. Now, if I take my 30,800 and I divide by 8.314, I get negative 3704.59. I'm going to take that and multiply that by both of the terms in here. So I'm going to multiply that by 1 over 353.1 and 1 over T1. And if I do that, I'm going to get negative 10.4916. Let's tweak that. There. Plus 3704.59 over T1. Come on. There we go. So if I add 10.4916 to each side, I'm going to cancel that out here, and I'll isolate my variable term, my T1. So that gives me 11.002, and that equals 3704.59. So now I'm going to multiply both sides by T1 and divide both sides by 11.002. And that's going to give me 336.7, or out of all the answers there, you'd round that up to 337 Kelvin as our other temperature. Okay. Back to the exam. So answer A for version A there, 337. Student collected multiple data points relating to temperature and pressure of a substance. She then plotted 1 over temperature versus natural log of pressure and obtained a straight line plot with a slope of negative 8,101. What is the enthalpy of vaporization of the substance? So this student made a Clausius-Clapeyron plot and then got a straight line plot with multiple data points and then had to get the slope, the equation of the line, and from that they want us to figure out the enthalpy of vaporization. The slope for a Clausius-Clapeyron plot is equal to negative HVAP over R. So if we take our slope essentially, multiply it by negative R, we're going to get our enthalpy of vaporization. So in this case, our slope is negative 8,101. We multiply by 8.314 joules per mole Kelvin, and that should give us our enthalpy vaporization in joules per mole. Times 8.314, there we go. So we get 67,352 joules, or 67.35 kilojoules. Other versions had different slopes. So whatever the slope happened to be, 8,101, 6,101, you're going to multiply it by negative R in each instance. Get your answer in joules and convert to kilojoules. So in this case, where is that? This instead, there. So in this version, answer is B. All right. Portion of the phase diagram for uranium hexafluoride is shown below. Which statements are correct? So the first one says that UF6 evaporates at atmospheric pressure. Well, atmospheric pressure is 1 atmosphere. So if I follow that out, if we start at a low temperature and go to high or vice versa, we're going to see that we start as a solid, but the line doesn't interface with the liquid portion. It interfaces with the gas. So, at atmospheric pressure, it's not going to evaporate. It would sublime. And then at 40 degrees C and 2 atmospheres, so 40 degrees C, back behind this 50 degrees and 2 atmospheres, somewhere right in here. And it says that the gas is the predominant phase, but we're right in this first chunk here, which is a solid phase. So the gas is not the predominant phase, solid would be. So in this case, neither 1 nor 2 are true or are correct. How much energy must be removed from a 125-gram sample of benzene at 425 K to liquefy the sample and lower the temperature to 335 K? The following physical data may be useful. So we have our melting and boiling point there, and then on the last page of that, we actually have some constants, our various enthalpies and specific heats. So there we go. So we're actually starting at 425. And in that case, we can see we're above the boiling point at 353. So we start as a gas, and it says we're going to cool it, or we're going to remove heat. So we're going to bring it down. And in this case, we're going to bring it down to the 353 degrees, which is the melting point. We go below that, we go down to 335. So that means we're going to take all that energy that we're pulling from it. We're going to take it from a gas to a liquid. And then we're going to cool that liquid a little bit further down to 335 K. So we actually have 3 segments here, and we're going to go on the chart technically segment 5, 4, and 3. So we need to find out what's the energy associated with each of these. So let's start with that first one. So for the first one, we're staying as a gas. We're cooling the gas. So I'm going to take the Q equals MCAT equation. So my heat is going to be equal to the mass, 125 grams, times the specific heat. In this case, it's the specific heat for the gas of benzene, which is 1.06 joules per gram degrees Celsius. And then times the change in temperature. We're going from 425 down to 353, that's 72 degrees C. So if I multiply all those by each other, I get 9,000 540 joules or 9.54 kilojoules. That's our first segment. Now the next part, we're converting from the gas to the liquid. So I need to go from mass to moles. We're just going to do Q equals moles times, in this case, the enthalpy of vaporization, or it'd be the opposite of this, it'd be condensation. So technically a negative value, but they want to know how much energy we're removing. So we can sort of compensate for the negative based on the wording of the equation. So I take the 125 grams, I divide by the molar mass, 78.11, gives me 1.60 moles, and we're going to multiply by the enthalpy of vaporization, which is 33.9 kilojoules per mole. We get 54.25 kilojoules. And then the very last segment, we're going to cool the liquid slightly. So we go back to our Q equals MCAT equation, same amount, 125 grams. Now we're a liquid, so I need to use the specific heat for the liquid, 1.73 joules per gram degrees Celsius, and then times the temperature change. Here we're going from 353 down to 335, our ending temperature, which is 18-degree change in temperature. That gives us 3,892.5 joules or 3.8925 kilojoules. And then just add them all together. 9.54 plus 54.25 plus 3.89. And we get 67.68, or out of the answer choices there, 67.7 kilojoules. Okay. So for this version, I'm looking at answer C. Identify the characteristics of a basic cubic cell, same as a simple cubic cell. So we just have atoms at the corner, 8 corners, 1/8 of an atom inside. So 8 times 1/8 is 1 atom inside, and a coordination number of 6 that it can coordinate to. The other cubes, one above, one below, one along the x-axis, and the other essentially along the z-axis. Metal crystallizes in a body-centered cubic structure and has a density of 7.83 grams per cubic centimeter. If the radius of a metal atom is 124 picometers, what is the identity of the metal? So we're going to go back in here. All right. So we know we've got body-centered cubic. So I know my edge length then is going to be 4r over the square root of 3. I know we're going to have 2 atoms inside the lattice cell, and we're given a density of 7.87 grams per cubic centimeter, and our radius is 124 picometers. So much for trying to write small. There. So I would start by figuring out the volume of this and then using the density to find the mass. You could go start with the atoms if you wanted instead of find moles, but let's just start there. So our radius is 124 picometers, so 4 times the radius. I'm going to convert that into centimeters, should be 1.24 times 10 to the negative 8 centimeters. And that whole thing is going to be over the square root of 3. Why won't you? What in the world? That's weird. 4.124 substances. So, that gives us an edge length of 2.8637 times 10 to the -8 centimeters. And then if I want to find the volume, I'm going to take the length times the width times the height. They're all the same, so I'm just going to cube that value and get 2.348 times 10 to the -23 centimeters cubed. Now I can take that value and multiply it by the density. That's going to cancel out my volume term and leave me with the mass term. So we'll know how much mass is present inside a single lattice cell. And that is 1.8483 times 10 to the -22 grams. So now if we can find out how many moles we have, put grams over moles, find the molar mass, and find out on the periodic table what substance we have. So we have a body-centered cubic. That's 2 atoms contained within there. If we divide by Avogadro's number, that's going to tell us how many moles we have. That is 3.321 times 10 to the -24 moles. And now put mass over moles. So 1.8483 times 10 to the -22 grams over 3.321 times 10 to the oh my God. 10 to the -24 moles, and that gives us 55.65 grams per mole, very close to the molar mass of iron, much closer than it is to any of the other substances there. So there we have answer B. Which of the following forms a molecular solid? CaCl, calcium chloride, that's ionic, so that would be an ionic solid. Au is gold, that would be a metallic solid. Carbon, solid carbon in specific graphite structure would be a network covalent. HCl, that's a molecule, and our interactions would be between one molecule and another, so that would be our molecular solid. Fe would be a metal again, that would be a metallic solid. So the answer there would be D. Define solubility, the amount of a substance that will dissolve in a given amount of solvent. So however, whatever that solute is, how much of that we can dissolve into the solvent, be that a solid into a liquid into a liquid, a solid into a solid, whatever. That's our definition of solubility. 15. Naval brass is 60.5% copper, 37.5% zinc, 1.8% tin, and 0.7% lead. Identify the solute or solutes in this alloy. So this is, again, a solution. It's an all-solid solution in this instance, but the solvent is our majority component, which would be the copper. It's present in the largest amount. And then everything else in this instance would be a solute. So that would be zinc, tin, lead all together. So the answer there would be E, which are B, C, and D. On a phase diagram, the vaporization curve is between the liquid and the gas. So those are just the vapor curves we studied initially of ethanol or isopropyl alcohol, water, ethylene glycol, and just looking at that specific interface between the liquid and the gas. Identify the type of interaction between atoms in a non-bonding atomic solid. So non-bonding atomic solid would be a single atom and they're not actually bonded. The noble gases are a really good example of this. So if we have neon and neon at all our lattice points, and then they're not actually bonded, we don't have intermolecular forces, we only have intermolecular forces, and the types of forces present there would be weak dispersion forces. Otherwise, we'd be looking at metallic solid or a network covalent or something like that. Which of the following elements would you add to germanium to make an N-type semiconductor? So an N-type semiconductor, we need to dope it with something that has more valence electrons. So with germanium, we're looking at being in row 4A. So this is below silicon. We have 4 valence electrons. So if I look at indium, that has 3, silicon, that has 4, gallium, that has 3, but arsenic has 5. So arsenic is the thing that we would dope this with to give us our N-type semiconductor. Identify the element with the largest band gap, so the biggest space between the conductance band and the valence band. Remember, metal should be pretty much no space, so we can throw out lead and tin. Silicon and germanium are semiconductors, so we will have some band gap there, but carbon is not a semiconductor. It's a full-fledged non-metal, so it should have the largest band gap. And then lastly, which solid would you expect to have the highest melting point? So I have Li, lithium, that's metal. I have ethanol, liquid with hydrogen, or it doesn't necessarily be a liquid, in this case it's a solid, but it has hydrogen bonding. Argon, that's a noble gas. Neon, that's a noble gas. And H2O, that's a molecule with hydrogen bonding. But out of all of these, so essentially I have non-bonding atomic for argon and non-bonding atomic for neon, and I have molecular solids for B and E, but I have a metallic solid for A, so I would expect that to have the highest melting point. Hopefully this helps. Hopefully this answers most of your questions. I know the sound quality of these hasn't been great. I switched out to a new computer, so I may need to get a mic or something so these get better, but hopefully you can at least hear me and understand me. If you have any questions, don't hesitate to ask. If you think there is an error on your Scantron, stop by any of my office hours. We'll pull the Scantron. We'll check that. Or if you want to know, exactly which ones did you get wrong, again, feel free to stop by my office hours. Go over the Scantron. We can work these in greater depth if you have a particular one that you still aren't sure about. Otherwise, I'll see you in class tomorrow. Bye.